Now, reviewing this illustration, we'll review the calculation procedure using the resistivity of a conductor. In step 1, 100 foot, we show a number 4 at 0.308 is our resistance. And then notice the resistance for a 100 foot run is divided by 1,000 foot because that's what the table 8R9 is based on. So 1,000 foot into 100 foot times the 0.308 resistivity of the number 4 conductor, we come up with a total value of 0.0308 when we do our math. Now, the branch circuit conductor number 12 for 100 foot, we have a number 12 AWG copper, 1.93 is the resistance. A 100 foot run divided by 1,000 times 1.93 for that number 12. We come up with a total resistance of 0.193. Now, we look at the current flow if we didn't have an equipment ground, and you would have 5 ohms at each grounding connection, one at the transformer, one at the service. And when we took the 5 and 5 ohms, added them together, given 10, 10 into 120, you'd have approximately 12 amps trying to flow through the earth to those, between those two grounding points. So we know the amount of fault current will not normally flow. It will usually be much less because it's using the earth as a path, and that's what the note 4 is illustrating. Now, next, we will look at the next illustration and see how the whole calculation goes together. Now, we were just showing you the method of using the table so far.